Good morning, everyone. My name is Kevin Trenberth. I'm coming to you from Auckland, New Zealand, and I'm going to talk to you today about climate change and the fact that climate change is already happening and some of the consequences and what we might do about it. So we're coming from planet Earth here, looking from the moon, and it appears that indeed the planet is warming up. This is a picture of me taken just a few days ago, and so I think that's enough of that. And this is where I am located at Auckland, New Zealand now. It's a long way from Malaga in Spain, and in fact it would take 3 flights, 27 hours of flying time, and it would have a huge carbon footprint. And so I have chosen not to come to Malaga, but rather thrust this recording on you, and so I hope I'll be available to answer questions at the end of the talk. So I'm going to begin with a few slides from the Intergovernmental Panel on Climate Change, the IPCC. They have had 6 major assessment reports. The last one came out in late 2021 in November for the science, and then in 2022 in February for the adaptation report, and in April for the mitigation report. And so I'll begin with a few slides from the PowerPoint presentation from the science report in November. This is the first slide, which says, "Recent changes in the climate are widespread, rapid and intensifying, and unprecedented in thousands of years." They go on to say, "Unless there are immediate, rapid, and large-scale reductions in greenhouse gas emissions, limiting warming to 1.5 degrees C will be beyond reach." And so there's some key statements here. Immediate, rapid, and large-scale reductions in greenhouse gas emissions. Well, none of those things are happening, are they? And so limiting warming to 1.5 degrees C is in fact beyond reach, I believe. And I think we will go through 1.5 degrees C increase in temperature, global mean temperature, from pre-industrial times, probably about 2032. It is indisputable that human activities are causing climate change, making extreme climate events, including heat waves, heavy rainfall, and droughts more frequent and severe. And I'm going to talk about why this is the case in most of this talk. So climate change is already affecting every region on Earth in multiple ways. The changes we're experiencing will increase with further warming. So with that, I'd like to talk a little bit about my own research thrusts. And I have focused on energy and water, and that'll be the theme of a lot of the rest of the talk here. And so we're dealing with the energy on Earth, and so we have the climate changing because of increases in greenhouse gases, and carbon dioxide in particular, which creates an energy imbalance. And the way in which it does that is because the carbon dioxide provides a blanket which reduces the outgoing long-wave radiation, and so the planet has to warm up until the temperature increases to increase the outgoing long-wave radiation so that it matches the absorbed solar radiation. Now, there are many feedbacks and complexities along the way, but one can argue that the most fundamental measure that the climate is changing is Earth's energy imbalance. A major advantage of this, compared with climate modeling, for instance, is that it's the net result of all of the complicated feedbacks. Now, I have a book which was published earlier this year, The Changing Flow of Energy Through the Climate System, by Cambridge University Press. It has on the cover the picture from November 5th, 2020, featuring Hurricane Ida, and there's some facts about the book there, 128 figures. There are very, very few equations, and they're all in sidebars so that you can avoid them. It's intended for people who are reasonably well educated on these topics, but perhaps not technically inclined. And I can get you a discount if you send me an email. And so to begin with, we'll start with the increasing carbon dioxide in the atmosphere. This is the record from Mauna Loa. It has a sawtooth character to it that you can see going up and down. It goes down in the spring and in the summer when photosynthesis in plants green up the plants and take carbon dioxide out of the atmosphere, and then in the fall and in the winter the carbon dioxide increases as the leaves and twigs and so on decay on the forest floor. But in addition, there is this huge increase, and it's increasing, the rate is actually increasing over time. And so I'll show that by putting a few arrows here as to indicate the rates of increase at different points. And indeed, you can see the rate is increasing right up to the present, and that includes the period of the pandemic. I'll talk a bit more about why that might be the case a little bit later, in spite of the fact that people were driving less and flying less, and some carbon dioxide emissions certainly did decrease during that period. Well, where does carbon dioxide come from? This is actually a slide I borrowed from Al Gore, and it shows all of the main human activities that are contributing to this. The biggest sources are from industry and mining of various kinds, but also from agriculture and transportation. There's a couple of things in here that are more or less side effects, the forest burning and the thawing permafrost, which end up putting more carbon dioxide and methane back into the atmosphere, and so these provide very powerful feedbacks. So let's talk a little bit about tires. This is one of the topics of this symposium. It's spelled in two ways, spelled differently in the United States, and my understanding is that there's over 1 billion tires per year that are manufactured, and each tire takes about 20 liters of oil in the composition of the tire, and about another 8 liters in the manufacture of the tire. And so all of this waste that you can see here of old tires is an environmental hazard, and if we were to burn them all, it would be about 0.01 terawatts of heat, which is a huge amount of heat. And also it would generate 50 megatons of carbon dioxide plus a lot of noxious pollution. So that's highly undesirable, and it makes the case for recycling and using the tires in other ways, which is indeed what I believe this conference is about. So some key starting points. Firstly, carbon dioxide in the atmosphere has increased by 48%. It's mainly from burning fossil fuels. It's a greenhouse gas, so it produces global warming. And the climate is changing as a consequence. But it's really heating. The atmosphere is heating rather than simply warming. Of course, warming is a synonym for heating, but heating, as we will see, has much more implications that are valuable for understanding what is going on. So in 2009, my colleagues and I produced a figure like this. It's been updated a little bit on the global mean flows of energy through the climate system in the vertical. And I'm not going to go into all the details here. I just want to focus on the top of the atmosphere and the net. And you can see that there's some 340 or so watts per square meter coming in, over 100 going out. The difference is about 240 or so, but there's 239 that is emitted in the long wave radiation, the infrared radiation, leaving 0.9 watts per square meter as the Earth's energy imbalance And so this is what is producing all of the climate change that we're dealing with. And 0.9 watts per square meter is 460 terawatts. And so that's what I've got here on this slide. 460 terawatts is 460 with 12 zeros after it. Well, it's hard to conceive of just what that means. And so what I've done here is to put for you the total amount of electrical energy generation, which was about 5.7 terawatts in 2018. And so it's a factor of about 80 less. Another comparison is a Christmas tree light is about 0.4 watts, and so that's a factor of 2 or so Christmas tree lights every square meter of the planet. And what this means is that the direct effects of humans through heating and electricity use and industry and so on are small, except locally in cities, and it's mainly through the interference with the natural flows of energy through the climate system that matters. Now, another comparison is the 0.9 watts per square meter compared with the overall flow of energy through the climate system, the 240 or so, 240 coming in from the sun and 239 going out. And so it's very small in that comparison. So you can't go outside and say, oh, I can feel global warming. That's not how climate change is experienced. Instead, it has to accumulate, but it does because it's always in the same direction. So where does it go? Well, it warms the land and the atmosphere, so temperatures do increase. But it goes to heat storage in the ocean, which expands and raises sea level. It melts land ice, which raises sea level. It melts sea ice and it then has to warm the melted water. And the tricky part is that it evaporates moisture, and that feeds into rainstorms and cloud and has all kinds of potential effects that are responsible for all of the changes in extremes. And so we're going to talk more about that. But over 90% of it ends up in the ocean. The question is, how does it get there? An example with extra heat. Well, for the human body, if there's extra heat, we perspire, we sweat. And the evaporation of the moisture from the skin is what keeps us cooler. For homes, we can use evaporative coolers if we're in a reasonably dry climate. These are called swamp coolers, and again use evaporative cooling. And for planet Earth, this works because 70% of the planet is ocean. And so the heat goes into evaporating moisture rather than raising temperatures. Another example, when the sun comes out after showers, the first thing that happens is that the puddles dry up before the temperature increases. Well, that's a little bit oversimplified perhaps, but the whole point of this slide is to highlight the role of water in keeping things cooler, but it has consequences because it puts more moisture in the atmosphere. Now, this is the record from NOAA of the global mean surface temperature, and it shows the record with the zero line as the 20th century value, and I've also indicated the pre-industrial temperature on there. The overall temperature increase is about 1.1 degrees Celsius. For this particular record, the warmest year is 2016. There's a certain amount of raggedness. That raggedness is greater in the early part of the record, partly because prior to 1957, the International Geophysical Year, there were no observations over Antarctica and the southern oceans, and also the amount of data is a lot less. And so some of this is just poor sampling, but some of this is real. These were El Nino years. This is an El Nino year. The warmest year on record is an El Nino year, 2016, and my pointer is stuck. And so let's now look at the carbon dioxide record. So this is the annual values of carbon dioxide, and the pre-industrial level is indicated there. Again, the zero line is the 20th century value, about 320 parts per million by volume. The pre-industrial is 280, and we're now at about 415 parts per million by volume. And I put them together in this way to suggest that there's a relationship, because we can indeed prove that there is. And about half of the increase in carbon dioxide has occurred since 1985. So this is during the time when all of you have been alive and contributed. So what about the atmosphere? Well, the warmer air holds more moisture. It's a rate of about 7% per degree Celsius, and that means that with global warming, with more heat available, that contributes to more drying and more evaporation and more moisture in the atmosphere. And in places where it is raining, the rain is therefore heavier, but in places where it's not raining, the drought sets in more quickly and is more intense, and the drought becomes more extensive. So this is my attempt at fancy graphics. I've got a little cloud here, and in the atmosphere, the air is often going up and down. It goes up if it hits a mountain because of the winds, or in weather systems of different kinds. And when it does, it expands in the lower pressure and cools, and therefore it can't hold moisture anymore, and so suddenly it rains like hell. And so the key point here is that it doesn't rain everywhere. It rains over about 11% of the planet at any time. And most of the rain that occurs comes from weather systems reaching out and bringing in the moisture from the surrounding environment into the cloud in this manner here. And as a result, if there's more moisture in the environment, it means that it rains harder. And this is responsible then for the heavy rains and the flooding. And at the same time, when that moisture condenses, it releases latent heat, the heat that went into evaporating the moisture in the first place, into the cloud, and it creates more buoyancy and strengthens the rainstorm itself. And so this is summarized in this graph here, indicating the increases in greenhouse gases, the heating. The heat goes into raising temperature, which increases the water holding capacity of the atmosphere, but a lot of the heat goes into increases in evaporation if moisture is available, and together these increase the actual moisture content. And so all of these weather systems feed on the available moisture, so we get enhanced precipitation rates, enhanced latent heating, and therefore enhanced storm intensity. And so this is what is happening in our climate system. Now, another place that effects accumulate are in melted ice. And we can see a lot of examples of this nature here, where there are sort of before and after pictures of the ice distribution. And down below I've got the Arctic sea ice, which has decreased by over 40%, near the minimum in the summer. This is the September record. Certainly there's natural variability there, but the overall trend is relentless. So what about ice sheets? So here I'm showing Greenland and Antarctica. This is an estimate of the melt you can see around the edges of Greenland, and it's also melting in the West Antarctic ice sheet and Antarctic Peninsula area. But over East Antarctica, there's actually a buildup of snow and ice because of the increased moisture in the atmosphere. And so Antarctica, we get about 2 terawatts of energy is going into melting Greenland, and about 1 in Antarctica. So what about land? Well, if land is wet, the heat goes into evaporation. But in a drought, the heat accumulates. And so we get, firstly drying and wilting of plants, and then heating, increases in temperature, heat waves. And so if we have 0.9 watts per square meter over a month, and we accumulate that, that's equivalent to about 700 watts per square meter over an hour. And 700 watts is the equivalent of a small microwave oven, and 1 square meter is about 10 square feet. And so this is equivalent to 1 microwave oven at full power for every square foot of the planet for 6 minutes. Well, you know, you can boil water in one of these little microwave ovens in about 3 minutes, and if you put paper in it, it'll catch fire, and so will the environment, and so wildfires are apt to increase. So what about the oceans? Ocean heat content. Well, since about 2005, we've had an observing system called Argo. These floats reside about 1 kilometer depth. They go down to 2 kilometers and they pop up to the surface, and they take measurements of salinity and temperature as they do so, and at the surface they then telemeter that information back to satellites and so to ground-based stations. And there's over 2,800 of these distributed around the world, with some 49 countries contributing to the deployment and the actual buoys themselves, the floats themselves, and it's producing new information for the top 2,000 meters of the ocean. And so we've been able to use that information to also use the more Spartan distribution of observations in earlier years to go back to the IGY. And this is the record of ocean heat content. This is through 2020. And not much change in the first part of the record, but we can see for the top 500 meters that it starts warming after about 1980. For 500 to 1,000 meters, it starts warming after the early 1990s. From 1,000 to 1,500 meters depth, it starts warming obviously in the late 1990s. And below 1,500 meters, it's around 2005. And so it takes, 30 years or so for the heat to penetrate about 2 kilometers into the ocean. So the ocean is slowly warming, but it is indeed a slow process. And now what I'm doing is showing the recent record for the ocean heat content. This is the same record here, annual values, versus the global mean surface temperature. You can see the global mean surface temperature, not much happened. This is the period where there was a pause in warming, and then we shot up and broke all the records with 2015, then 2016, and fairly high values in recent years. And this was a major El Nino, and as a result, the global mean surface temperature is fairly irregular compared with the ocean heat content, which is much more regular in terms of the overall warming. Now, there are small changes that occur. This is especially during El Nino. Heat comes out of the ocean and contributes to the heat in the atmosphere, and so, but it's relatively small in terms of the ocean heat content. So the ocean heat content turns out to be one of the best indicators that the planet is warming, and of course that contributes to sea level, which we'll show in just a minute. One of the consequences of increases in ocean heat content are increases in marine heat waves, and this is a documentation of major marine heat waves that have occurred in the past couple of decades or so. This is El Nino related here. One of the worst was in the North Pacific here, called the blob, and over 100 million cod died as a consequence of that, along with changes in the phytoplankton and the zooplankton and the fish and marine mammals, otters and seals and whales, and also birds, seabirds. Tremendous mortality that occurred in conjunction with that event. And similarly, different kinds of things down here around New Zealand and in other places around the world, even including in the Mediterranean. Now, one consequence of both the glacier melt, the melting of Antarctica and Greenland, and the ocean heating through the expansion of the ocean is sea level rise. And so these are from altimeters in space from these different satellites. Topex Poseidon was the first one, and the rate was about 3 millimeters per year for the first part of the record, but now it's up around 4 to 5 millimeters per year. And so it's over 90 millimeters increase since 1992, and about 47 millimeters of that is because of the expansion of the ocean. And so the synthesis overall in terms of the heating of the planet is that the atmosphere takes up about 0.6%, 3.4 terawatts. The land warming, including The thawing of permafrost is about 3%, 16 terawatts. The ice total is about 2.4%, 11 terawatts. And so the non-ocean is about 30 terawatts. And then the ocean is 430, which is 93% of the total of 460 terawatts, which is 0.9 watts per square meter for the total planet. And so we've been able to account for this overall, and we've got some good indications of changes from year to year, but not so much for land and not as much as we'd like for ice, especially in Antarctica. And so this is a summary of what we've just dealt with here. Increases in sea level. There's an increase in stratification because the ocean warms from the top down, and so it becomes more stratified. That affects the penetration of nutrients and oxygen into the ocean, and it affects all of the wildlife in the ocean. There's coastal erosion because of sea level rise and coastal flooding in particular, saltwater intrusions into water systems, the ice is melting, and then there are the consequences we've seen in the atmosphere. Well, what about the changes in extreme? We've hinted that because of the changes in the water cycle, that these are indeed profound, and they matter most for society and human health. And with a warming climate, we have higher temperatures, heat waves, wildfires, and other consequences. And we have fewer cold extremes, but in particular, there is more intense rainfall and snowfall even, and longer dry spells. And so the management of water becomes a major issue along with all of these extremes that we're going to talk about a bit more now. And so what about typhoons and hurricanes? Well, these are natural phenomena, and here I put this slide together originally around 2019, and so I documented all of these major storms that occurred in 2017, 18, 19, and hurricanes are natural, but they're now supersized, and I don't think any of them would have occurred the way they did without the human-induced climate change. And they've been further exacerbated by poor preparedness in most cases. The damage occurs because of the wind-related damage and flying debris and coastal storm surges, and also the heavy rains and flooding can extend quite a long way inland. So we'll illustrate that a little bit. With climate change, we expect more intense hurricanes, bigger hurricanes, longer-lasting hurricanes, and more flooding rains. So here's an example from 2020. This was when there was an absolute bombardment of tropical storms and typhoons into Vietnam in particular. Tremendous activity in that region, and some absolute devastation occurred there. In the Atlantic, spectacular pictures like this with a whole host of storms that occurred in 2020, and by late November there had been 30 named storms, a record, and so we ran out of names in the alphabet and had to go to the Greek alphabet. Now, one of the biggest storms was Ida, and there's some statistics here related to Ida, something like $100 billion in damage. There was very high ocean heat content in the Gulf, and a lot of damage occurred as it made landfall there. But some of the biggest damage occurred as it moved northwards, right along the East Coast and in the New York area. Here's New York, and there was over 10 inches of rain, over 250 millimeters, over quite an extensive area with tremendous flooding, and the subways were flooded in New York City and many other areas. Just tremendous damage. And you can see why a little bit. Down here is the sea surface temperatures, and it was very warm all the way up the East Coast, and so there was warm, moist air being fed into this storm. Well, another consequence later in 2020 was in the southern hemisphere when Yasa occurred, and in the Fijian Islands, you can see the Fijian Islands right here. Here's the eye right in the middle of all of these islands, and absolute devastation occurred. And so we can see that here with, you know, the value of the infrastructure may not be something to write home about, but the damage was just tremendous, and the damage to all the crops and the devastation and disruption of all of the lives in the Fijian Islands was just tremendous. And, you know, dollar amounts simply don't do it justice. So what about floods? And maybe a little bit on heat waves and wildfires here. This was, again, a 2019 slide originally, and so there were a lot of examples of problems in various parts of the world. And then there was major flooding in Japan in the first part of July in 2018. In the second part of July, it broke all kinds of records, over 40 degrees Celsius with heat waves. Meanwhile, California wildfires were setting a record at that time, and also Brazilian wildfires. But then in 2021, there was more flooding, not that far away from where you are now, in Europe, and also major flooding in China and the subway there, which caused quite a large loss of life there. And, you know, a bit later in Mumbai in India. And, you know, I put 3 separate events in different locations in New Zealand where there was extensive flooding. You probably didn't hear anything about that, but it still had a major impact here. Well, there is in March 2022 major flooding in Australia, and you can see the storm here. It doesn't look that impressive, but nonetheless, over 790 millimeters of rain in the week up to the 28th of February, and a tremendous amount of flooding occurred and damage in Australia. Then maybe a similar kind of event in a way, not a very impressive looking storm, but huge flooding in the southeast part of South Africa, and you can see some of the devastation here with over 443 people losing their lives in that particular event. Back in 2019, there were major wildfires. This was a weak El Nino event, and so El Nino, major dry and drought and wildfires in Australia, and then, you know, this past year, La Nina is when the flooding occurs. And so here's the wildfires, and you can see the picture from space with all these plumes heading across towards New Zealand. And I was in Auckland. We had 2 days where we completely blotted out by smoke from these wildfires. And this is, what, some 1,200 miles away from Australia. In 2020, there were a major number of wildfires again in California, with a lot of damage that occurred and smoke that was seen in Europe as a consequence. And there's estimates of even how much went into the atmosphere. And of course, this is the thing which occurred in spite of the pandemic that put more carbon dioxide into the atmosphere. And it's one of the reasons why the carbon dioxide concentrations continue to go relentlessly upwards. In 2021, it again broke records, and you can see down the bottom here the records of the drought monitor, with records in 2021 in the southwestern parts of the United States and in Los Angeles County. You can see the change from space from June of 2020 to June of 2021, the drying up of lakes, all of the wildfires, and it extended up into San Francisco area, Napa Valley, all of the wines and the wine cellars. What a tragedy. And you know, Lake Mead is one of the major lakes in the southwest that has lost just about all of its water. Now further, in 2021 in July, there was a major event, a really exceptional event that wouldn't have occurred without global warming. And there was a big heat wave, a heat dome in the Pacific Northwest, especially in southwestern Canada. This is actually in Portland, Oregon, and you can see the dots show individual months over time and in days over time. And this is the 3 days during 2021, well outside of any previous records. And then this poor town of Lytton, where the temperatures got up to 49.5 degrees Celsius, The town was destroyed with a fast-burning wildfire 2 days later. Really tragic. So heat waves occurred elsewhere in Turkey with wildfires, and also in Greece, and extensively in Siberia. Many wildfires in Siberia. So it's not just the United States and so on. And then there were blistering heat waves just recently in March through May in India and Pakistan. So this extends to the Pakistan border. And some of the damage you can see here. And there was a study very quickly done which suggested that the deadly heat wave was made 30 times more likely by the global warming. So the costs of climate change. Climate change is happening. It's caused by human activities. And for many events, based upon the changes in water vapor in the atmosphere, we can estimate that the effects of climate change are of the order of 5 to 20%. But this means that thresholds are crossed and records are broken. And so what happens is that things go non-linear. And the extreme non-linearity is where things break, where things flood, places flood, where properties and vegetation burn and people die. You don't recover from these things. And this is the sort of thing which drives economists crazy. They can't handle this kind of thing. And as a result, they underestimate the impacts of climate change. But instead of, small hurricane producing $1 billion in damage, the damage is now $100 billion in damage. I showed you one example from Ida. And so this is what I call the straw that breaks the camel's back syndrome. Well, in April of this year, Working Group 3 of the IPCC looked at all the mitigation options and suggested that there were indeed options in energy, land use, industry, in cities, in buildings, in transportation that could cut emissions in various ways, and they made a bunch of recommendations. They suggest that we have the tools and the capability to hold climate change in check, but what is missing is the political will. Moreover, it can be done equitably and cost-effectively, and so this is really an ethical problem, and they suggest that the future is in our hands. Well, I addressed this a little bit in my book, and I referred to Yogi Berra, who's a famous baseball player, and he said, baseball is 90% mental and the other half is physical. I suggest that on climate change, he might have said, climate change is 90% ethical and the other half is science. And a lot of what we've talked about here is the science. One of the other slides they presented in the Working Group 3 presentation was this one here, and I put it in here because down the bottom of the slide there is a whole bunch of old tires, very much the subject of this symposium. And you can see they make various suggestions here that using materials more efficiently, reusing, recycling, minimizing waste, currently underused policies and practice. And so this is, of course, where rubberized asphalt comes into play as a form of recycling of all of these old tires. There was a recent report in Nature by Housefather and Moore where they did an overall summary of what the IPCC was showing. And so this is the past global mean surface temperature record. And the IPCC report had quite broad possibilities going into the future without making a preference as to what the best guess was. And these guys had an attempt at doing that. And they suggested that this is the most likely range of what is likely to occur. And with current policies, we would end up here at about 2.7 degrees Celsius above the pre-industrial levels in 2100. With net zero pledges, then we could perhaps get down to 2 degrees Celsius. And so they suggest that this is possible. However, I've suggested to you that these, current policies, it's all very well to have a policy, but they're not being implemented. And the net zero, I don't see the progress towards net zero that needs to happen. And so we're going to cross 1.5 degrees somewhere around 2032. And at the current rate, we will go through, 2 degrees Celsius somewhere around the 2050s or thereabouts. So the options are there with the right kind of actions to not go through 2 degrees Celsius, but at the moment we're headed in that direction. And so climate change is happening. It's caused by human activities. It already costs tens of billions of dollars per year in damages. And so these are the two things that we can deal with. Mitigate it, which means stopping or reducing emissions. That's the Working Group 3 report. We can adapt to it and plan for the consequences and build resiliency into the system. I didn't go very much into that. This is all dealt with in Working Group 2 of IPCC. And we can do nothing and suffer the consequences. And unfortunately, that's most of what we've been doing. So rubberized asphalt has a role. My best wishes to you all for a great conference. I want to thank George for inviting me to give this talk, and best wishes on a good conference. This is my contact information. Thank you very much.